The explanation to the results we have just seen passes through a clear use of statistical estimation theory. Therefore, we describe the fundamentals of this field first, and then we'll bring them to SparseLand. Our entire story revolves around the desire to estimate a specific signal x, which we have no access to. Instead, we get a measurements vector z related to it somehow. The relation between the two is quantified by the following two very different conditional probabilities: the probability of z given x and the probability of x given z. Statistical estimators aim to use these conditionals in order to infer x from z. We have to be fair and say that in many problems in signal and image processing, formulating the conditional probability is by itself the biggest challenge. Here we will simply assume that these functions are given. The probability of z given x is also known as the likelihood function. This function considers x as a set of deterministic parameters that govern the probability of z. The maximum likelihood estimator suggests to maximize this function with respect to x in order to discover the desired signal. The maximum likelihood, ML for short, is very popular, but sometimes it is too weak or even useless. For example, when denoising a signal from additive Gaussian noise, the ML would suggest the noisy signal as our estimate, which is clearly far from anything satisfactory. In such cases, we turn to the richer Bayesian approach. The migration from the ML to the Bayesian approach is all about changing the order of the elements in the function p. Now we consider the probability of x given z. This may sound like a trivial change, but in fact it represents a huge philosophical leap in our view of the estimation task, because now we think of x as random as well. Why do we call this the Bayesian approach? Because we can invoke the Bayes rule in order to see the connection between the two conditionals as shown in this expression. The maximum a posteriori probability estimator, MAP in short, suggests to estimate x by maximizing the posterior probability p of x given z. Due to the Bayes rule, this is equal to maximizing the likelihood function multiplied by the probability of x itself. So MAP is different from the ML due to the involvement of p of x. By the way, why have we omitted the denominator from the Bayes formula? Because it is independent of x, and thus it does not influence the estimation process. We have just defined the MAP estimator. Described verbally, it searches the most probable x given the measurements z. And if you think about it, this describes our situation more faithfully, as z is given and x is the unknown. When migrating from ML to MAP, we bring in the influence of p of x. We call it the prior, and we have discussed this in depth already in the beginning of our course when discussing signal models. We emphasize that MAP is just one way to practice the Bayesian approach, and other estimators using p of x given z do exist. Indeed, here is another Bayesian estimator called the MMSE estimator, which stands for the minimum mean squared error. We are given the posterior p of x given z, and we would like to estimate x from it. What could we do? Well, if our estimator is x hat, then this expression is the expectation of our error, which is nothing but the squared L2 distance between x hat and the original x, multiplied by the probability of x given z, and integrating over all the x's. We can take a derivative of this error with respect to x hat and seek the optimal solution leading to the smallest average error. This is the derivative, and from it we get the MMSE estimator. Observe that it is relying on the posterior probability. This is the conditional expectation of x given z. Let me give you a little bit of intuition about the two estimators we discussed, the MAP and the MMSE. If this is a 1D function that describes p of x given z, then its peak points to the MAP estimation. Its mean leads to the MMSE estimation, which is necessarily better in terms of the mean squared error. In some special cases, the two estimators align. This takes place when the probability function is symmetric, for example. In image processing, we hardly meet the minimum mean squared error estimation, since it involves a massive and high-dimensional integration. This explains the popularity of MAP in our field. Nevertheless, MMSE is always there, hiding in the dark. Sometimes we stumble on it without really noticing.